Okay, um, so now we know that we have in the region x is less than 0, that is to the left of the potential step. Okay, so in this region over here, okay, then we have both right moving and left moving solutions, and in the region to the right of the potential of the step, that is x is greater than 0, we have only right moving solutions only. And so um, the constant A is basically given by just knowing what the initial intensity, that is the number of particles per unit time of the beam is, okay, by this relationship that we already discussed, okay. And I should mention that we can choose, obviously, since a squared is the complex magnitude squared, okay, so it's a star a, but we can actually choose a to be real, and we can make that choice once. That basically just corresponds to choosing a phase shift in the plane wave, okay, and so it doesn't change anything physical. But once we choose that phase by making a real or not, but if we choose it to be real, then we don't have the freedom to choose any more phases. So then the constants b, c, um, and, and any other constants which come into any other phases which come into the plane, into the solution of the Schrodinger equation, that is for the wave functions, we're no longer free to choose. We can only choose the phase of one. Okay, and so that will give us the constant a. And now we want to apply the boundary conditions. And so what we recognize is that at x equals 0, at the position of the potential potential step, then for any of the oscillatory solutions, e to the plus or minus k times x equals 0 is equal to 1. Okay, and so what that means is that on the left-hand side of x equals 0, so on the left-hand side of the step, then we have that is equal to a plus b, and this must be equal to the right-hand side of the solution on the right-hand side of the step, and that's equal to c. Okay, so again, so we get a plus b is equal to c. All right, now we also have to have the derivatives, okay, of the solution on the left-hand side. This is the continuity equation for the slope. So the slope of the wave function has to be also continuous. This is equal to I times k1 times a minus I k1 times b, and this has to be equal to the the derivative of the wave function on the right hand side of the step, okay, and this is equal to I k2 times c. Alright, so again, so now we have I times k1 times a minus b is equal to I times k2 times c. So you can see we can cancel the i's. I think I did that right. Okay, so so now we can manipulate these two equations. Where again we know a, or at least it's not it's given by a different equation here, and so we only have two unknowns, actually b and c, and now we have two equations, so we can manipulate these. And what we're going to find is that they actually ratios give us the reflection and transmission coefficients for the particle to go past the step.